Hello everyone, I'm Jaydeep Saha, a research fellow at the National University of Singapore, and I'm going to present our paper on computational feasibility of multi-objective optimal design techniques for grid-connected multi-cell solid-state transformers. After a brief introduction, I'll talk about the solid-state transformer with DC bus and the scope of optimization there, the design optimization techniques, possible for such a solid-state transformers design optimization, execution of a ML-aided hybrid optimization technique, the comparative evaluation of the various possible techniques, followed by a brief conclusion. So the online tap changing transformers are quite common in the power system today. However, they have certain disadvantages in terms of failure to provide continuous controllability and bidirectional power flow, and are criticized for their bulky nature. And anyway, they need power electronic reinforcement for integration of renewable energy. On the other hand, solid-state transformer technology has been proposed as an alternative for the OLTC, and it consists of isolated power electronics converter on either sides of a medium frequency transformer. Studies in the literature have shown that medium voltage AC to low voltage DC conversion is economically justifiable, and there are few efforts in the literature on optimal design methodology of SSTs, but a comparative analysis of the optimization techniques are not provided, and that is exactly what we have presented in this paper. So the solid-state transformer, the DC bus is shown on the figure on the right. The DC bus is critical for the MV grid connected solid-state transformer because it provides perks in terms of economic justifiability, efficiency, power density, and cost, and also has to fulfill the functional necessities of a typical energy control center. It helps in the integration of renewable energy sources and energy storage, and restricts the propagation of disturbances from medium voltage side to low voltage side, and vice versa. The three distinct parts of the medium voltage AC low voltage CSST is the cell or the AC/DC submodule, the AC filter inductor, and the um, DC capacitor. However, the DC capacitor are mostly film capacitors these days, which are very uniform in efficiency and power density. So these are usually not considered for optimization, and the fixed model can be used for them. So efficiency and power density are the critical design objectives, and the objective of cost is usually not considered because due to regional variation in cost, the critical objectives of efficiency and power density can be jeopardized. And there's a very slim range of costs for MBSC, LVDC, SST, so there is not much value in including this objective in the design optimization. The design optimization framework is shown in this figure. On the left side, you can see the local optimization where various algorithms are used to optimize the design of the isolated AC-DC submodule and the AC filter inductor for a given subset of VB primary, which is the blocking voltage of the primary side second semiconductor devices, VB secondary, which is the blocking voltage for secondary side devices, and FSW is the switching frequency. Now, once this is done, then lookup tables or trained models can be obtained from this local optimization, and then for a continuous switching frequency, you can generate the Pareto curves. You can do the computation for loss and volume using these models or lookup tables and the fixed model for CDC, and come up with the Itero Pareto fronts. Now, the globally optimal SST design can be obtained by choosing a pertinent design specification on the various Pareto fronts that you get, and you have to choose the most superior of them that gives the best efficiency and power density. Now, most of the computational burden in the optimization framework is due to the local iter-row optimization, and this local iter-row design optimization can be uh, can be accomplished using three techniques. One of the techniques is the analytical one, which is based on computational and inexpensive analytical equations and yield closed form solution. But though it is intuitive, it suffers from lack of accuracy due to error-prone analytical models. Now, the semi-numerical or hybrid optimization technique is not entirely intuitive and does not have closed form solutions, and are two major types. First one is based on the analytical expressions, but the optimal design is obtained using numerical optimization routines. And the second one is based on combination of analytical and numerical models, and the optimization routine is intelligently employed to minimize the number of numerical computations. And this displays much better accuracies and are reasonably fast. The numerical optimizations are based on completely numerical simulations where each iteration is um, quite expensive computationally and is thus not a feasible technique. Uh, Now, the superior technique of some machine learning aided hybrid optimization is being employed by us for the design of a single stage cascaded matrix based dual active bridge medium voltage AC low voltage DC solid state transformer, and the optimization algorithm is shown here, and detailed derivation of the models and explanation for this optimization is given in our paper. So as you can see that after the local optimization, you would employ a ML algorithm here, and this ML algorithm would then train models that would help in the global optimization. So in various categories, the Pareto fronts are shown here, and the categories were previously defined here based on the VB primary and VB secondary. So we can see that in category B, it provides the best Pareto front, and the stars show the black stars show the various uh, mm, experimental results obtained at various frequencies for the prototype that is developed by us. And while operating at 20 kilohertz, it lies on the Pareto front, which is very near to the knee point of category B, which is the global optimal design. So the same 15 kVA, uh, same BDAB, which is considered for modeling and optimization, is also experimentally validated, and you can see that there's very less results. So I'll discuss that it provides less than 5% mean absolute percentage error. Um, so the comparative evaluation of techniques is performed by considering one data set at every 0.25 kilohertz, which is generated, and that leads to the total number of data sets, which is 768 in number, and a Dell i7 PC with 16 GB RAM is used. So the comparison of the computational burden and mean absolute percentage error of the various optimization techniques are provided here. That is the fully analytical one, the fully numerical one, the standalone hybrid one without any machine learning um, aid, and the machine learning aided hybrid optimization. So we can see that though the fully analytical one leads to very less computational burden and less computational time, but it leads to more than 12% mean absolute percentage error, which is the downside. The fully numerical one is estimated to take too much time, though it is expected to yield low errors, and is thus not feasible with the usual computational resources that a power optimized design engineer would have. Now, the standalone hybrid one also takes quite a lot of computational expense. The ML-aided hybrid one, however, takes a reasonable amount of time and can yield lower mean absolute percentage error, and it intelligently reduces the number of FEA compared to the without aid of machine learning one. So coming to the conclusion, the applicability of medium voltage AC solid state transformers is highlighted, and Why is it critical to have a DC bus? Also, the scope of design optimization, which components can be optimized, and the design objectives. These are well clarified, and the three possible optimization techniques, that is analytical, semi numerical or hybrid, and the numerical ones are discussed, and the emulated hybrid optimization technique is presented elaborately with the important component models, the routine and experimental validation. The comparative evaluation of analytical, numerical, standalone hybrid, and the emulated hybrid optimization techniques are compared for 15 kVA silicon carbide based MBS LVDC SST, and the emulated hybrid SST design optimization technique is adjusted as the superior solution, as it is low errors and requires reasonable computational time. Thank you very much for your attention.